Mars hangs in the night sky as a small red point of light, silent and distant. For thousands of years, humans have looked at this planet and wondered what it was. Ancient cultures associated it with war and fire, drawn by its color and motion across the heavens. Modern science gave it a new identity. Mars became the red planet, a cold desert world covered in dust, rock, and ice. A planet that appears lifeless and abandoned. But Mars was not always this way. Beneath its rust-colored surface lies evidence of a very different past. Ancient river valleys carved into stone. Dry lake beds stretching for hundreds of kilometers. Minerals that only form in the presence of liquid water. These discoveries reveal a shocking truth. Mars was once warm. Mars was once wet. And Mars may once have been alive. Today, Mars is a frozen desert with a thin atmosphere and brutal radiation. Liquid water cannot exist on its surface for long. The planet struggles to hold heat. Winds strip dust across barren plains. Its surface is hostile to life as we know it. But billions of years ago, Mars may have resembled early Earth more than it resembles itself today. Mars and Earth formed from the same region of the solar system. They share similar building blocks. Early in their histories, both planets had volcanoes, atmospheres, and flowing water. Both experienced geological activity and chemical cycles capable of supporting life. For a time, Mars may have been a habitable world. Something changed. At some point, Mars lost its magnetic field. Its atmosphere began to thin. Water disappeared from the surface, rivers dried up, lakes vanished. The planet cooled and faded into the cold desert we see today. Understanding how this happened is one of the most important questions in planetary science. Mars is not just a dead world. It is a fossil planet. A record of what happens when a world loses its ability to protect itself. Its surface preserves the memory of flowing water and a climate that once supported stability. Mars shows us that planets can change dramatically, even after starting with the right conditions. This documentary explores the forgotten history of Mars. We will uncover how rivers once flowed across its surface, how lakes and possibly oceans formed, and why the planet lost nearly everything that made it habitable. We will examine whether life ever emerged on Mars, and why scientists continue to search for its traces today. Mars is not only a destination for exploration. It is a warning written in stone. A reminder that planetary survival is fragile. And a clue to how life may rise and fall across the universe. Mars formed around 4,500,000,000 years ago, during the same violent era that shaped Earth and Venus. The young solar system was filled with debris. Asteroids collided. Planets grew through constant impacts. From this chaos, Mars emerged as a smaller sibling to Earth, but one that shared many of the same ingredients. Early Mars was very different from the planet we see today. Geological evidence shows that it once had a much thicker atmosphere. This atmosphere trapped heat more effectively, allowing the surface to remain warm enough for liquid water. Volcanoes were active across the planet, releasing gases such as carbon dioxide and water vapor into the sky. These gases helped maintain a stable climate during Mars's earliest period. At this time, Mars also possessed a global magnetic field. Generated by a molten core, this magnetic field protected the planet from solar radiation. It shielded the atmosphere from being stripped away by the solar wind. This protection allowed Mars to hold onto its air and water, creating conditions suitable for rivers, lakes, and long-lasting bodies of liquid water. Images from orbit reveal ancient river valleys carved deeply into Martian rock. These valleys branch and twist in patterns similar to river systems on Earth. They were not formed by brief floods or melting ice alone. They were shaped by flowing water that persisted over long periods of time. Some channels stretch for hundreds of kilometers, cutting through highlands and plains alike. Mars also shows clear evidence of ancient lakes. Large basins contain sediment layers that indicate standing water. These sediments settle slowly over time, suggesting calm lakes rather than violent floods. In some regions, Scientists have identified deltas, fan-shaped deposits formed when rivers emptied into lakes. These structures require sustained water flow and stable climates. Minerals found on Mars strengthen this picture. Clays, sulfates, and carbonates have been detected by rovers and orbiters. These minerals only form in the presence of liquid water. Their chemistry reveals that the water was not highly acidic or extreme. It was relatively neutral, similar to environments on early Earth where life emerged. All of this evidence points to a simple conclusion: Mars was once a water-rich world. It had rivers that flowed across its surface. It had lakes that lasted for long periods of time. It had a climate capable of supporting stability rather than chaos. For millions of years, Mars may have been habitable. It may have offered environments where simple life could emerge and survive. But beneath this stability, Mars carried a critical weakness. Its smaller size would eventually change everything. Mars may have looked stable on the surface, but deep inside the planet, its fate was already forming. Compared to Earth, Mars is much smaller. This difference in size shaped its entire future. Smaller planets cool faster. Their internal heat escapes more quickly. And when that heat is lost, the processes that protect the planet begin to shut down. Early Mars had a molten core. This molten core generated a global magnetic field, much like Earth's magnetic field today. That magnetic field acted as a shield. It deflected charged particles from the sun and prevented the solar wind from directly striking the atmosphere. As long as this shield remained active, Mars could hold onto its air and water. But over time, Mars began to cool. As the planet lost internal heat, its core slowly solidified. When the core cooled enough, the magnetic field weakened and eventually collapsed. This moment marked a turning point in Martian history. Without a magnetic shield, Mars became exposed to the full force of the sun. The solar wind is a constant stream of charged particles flowing outward from the sun. On Earth, the magnetic field deflects most of this radiation. On Mars, once the magnetic field disappeared, the solar wind began to interact directly with the upper atmosphere. Over millions of years, it stripped gas away molecule by molecule. Mars began to lose its atmosphere. As the atmosphere thinned, the planet struggled to retain heat. Surface temperatures dropped. Liquid water became unstable. Rivers that once flowed steadily began to slow. Lakes began to shrink. Ice formed more frequently. Evaporation increased while replenishment declined. This loss did not happen suddenly. It unfolded gradually across hundreds of millions of years. Mars did not freeze overnight. Instead, it faded. Volcanic activity, which once helped replenish the atmosphere, also declined as the planet cooled. With fewer eruptions, fewer gases were released. The balance tipped further toward loss rather than renewal. As atmospheric pressure dropped, water could no longer remain liquid for long on the surface. It either froze into ice or sublimated directly into vapor. Some water escaped into space. Some became trapped beneath the surface as ice. Mars was entering a slow death. The planet still held rivers and lakes for a time, but the systems that sustained them were weakening. Mars had crossed the beginning of its irreversible decline. Once Mars lost its magnetic field, the planet became vulnerable in a way that no surface feature could prevent. The atmosphere was no longer protected from the sun. Solar radiation and charged particles began stripping it away slowly but relentlessly. This process transformed Mars from a warm, wet world into a cold desert. As the atmosphere thinned, its ability to trap heat weakened. Carbon dioxide and water vapor escaped into space. Atmospheric pressure dropped steadily. With less pressure, liquid water became unstable on the surface. Rivers that once carved valleys across the planet began to dry. Lakes that once reflected sunlight began to freeze and vanish. Water on Mars did not disappear in a single way. Some of it froze into thick layers of ice near the poles and beneath the surface. Some sublimated, turning directly from ice into vapor and drifting away. Some was broken apart by sunlight in the upper atmosphere, allowing hydrogen to escape into space. Over time, Mars lost the majority of its surface water. The surface itself records this loss. Ancient river channels end abruptly. Lake beds show signs of evaporation and retreat. Minerals that form in water appear in older terrain but are rare in younger regions. These patterns reveal a world transitioning from wet to dry. As temperatures continued to fall, Mars entered a new climate state. Ice became the dominant form of water. Seasonal changes shifted frozen carbon dioxide and water ice between poles and mid-latitudes. Dust storms became more frequent as loose material was exposed on a dry surface. Without a thick atmosphere, Mars also lost protection from radiation. Cosmic rays and solar particles now strike the surface directly. This radiation breaks down organic molecules and makes long-term surface life nearly impossible. Any life that once existed would have needed to retreat underground or perish. Mars did not explode. It did not burn. It slowly faded. What remains today is a planet locked in cold equilibrium, thin air, weak gravity, frozen water hidden beneath the soil. Mars still holds the memory of rivers and lakes, but it can no longer sustain them. As Mars continued to lose its atmosphere, the planet did not become dry all at once. For a long period, liquid water still existed on the surface, collecting in low-lying regions and forming vast lakes. In some areas, the evidence suggests something even larger. Mars may have once had an ocean. One of the strongest candidates for an ancient Martian ocean lies in the planet's northern hemisphere. This region is unusually smooth and flat compared to the heavily cratered southern highlands. Scientists believe this lowland basin could have held a massive body of water that covered millions of square kilometers. Shoreline-like features have been identified along its edges, resembling coastal formations on Earth. Rovers exploring Mars have found compelling evidence of long-lasting lakes. In places like Gale Crater and Jezero Crater, layered sedimentary rocks reveal a slow and steady process of deposition. These layers formed as fine particles settled out of calm water over long periods of time. Some of these lakes may have lasted hundreds of thousands or even millions of years. Deltas provide some of the strongest proof. These fan-shaped structures form when rivers carry sediment into standing water. On Mars, deltas preserved in stone show that water flowed consistently in one direction, feeding lakes that remain stable long enough for thick layers of sediment to accumulate. These conditions are similar to environments on Earth where life thrives. Chemical analysis of Martian rocks reveals minerals that only form in water-rich environments. Clays indicate long-term interaction between water and rock at moderate temperatures. Carbonates suggest neutral or slightly alkaline water chemistry. These are not the products of brief floods or melting ice. They require sustained liquid water. During this period, Mars may have looked very different. With a thicker atmosphere and abundant surface water, the planet may have had clouds, rainfall, and a water cycle. Snow and rain may have fallen across its surface. Rivers may have flowed seasonally. Lakes may have expanded and contracted with climate shifts. This version of Mars was not Earth, but it was active, dynamic, and potentially habitable. The presence of stable lakes and possibly oceans means that conditions suitable for life may have existed for long periods of time. But this era was temporary. As atmospheric loss continued, the pressure dropped further, temperatures fell. Liquid water became increasingly rare. The lakes dried, the oceans receded. Mars entered its final transformation. The question of life on Mars is one of the most important scientific questions humanity has ever asked. Mars was once warm. It had liquid water. It had energy from the sun and from volcanic activity. It had stable environments that lasted for long periods of time. On Earth, these same conditions led to the emergence of life. There's no scientific reason to assume Mars was an exception. If life appeared on Mars, it would most likely have been microbial. Simple organisms similar to bacteria on Earth could have lived in lakes, rivers, or wet sediments. These microbes would not have required oxygen. They could have relied on chemical energy, using minerals and dissolved compounds in the water to survive. The best environments for early Martian life would have been long-lasting lakes and groundwater systems. These environments provide protection from radiation and stable chemistry. Many of the places explored by Mars rovers were chosen specifically because they once held water. Scientists search for biosignatures, chemical or structural patterns that could only be produced by life. Some Martian rocks contain organic molecules. These molecules are the building blocks of life, but they can also form through non-biological processes. Their presence alone does not prove life existed, but it shows that the chemistry needed for life was present. Scientists also look for patterns in minerals that suggest biological activity. On Earth, certain microbes leave behind distinctive textures and chemical ratios in rocks. Finding similar patterns on Mars would be a major breakthrough. So far, no definitive biosignatures have been confirmed, but research continues. As Mars lost its atmosphere and surface water, life would have faced increasing stress. Radiation levels rose. Temperatures fell. Surface environments became hostile. If life existed, it would have needed to retreat underground, where water and protection from radiation might still exist today. This possibility drives modern exploration. Rovers drill into rocks, analyze ancient sediments, and search for signs of past life preserved in stone. Future missions aim to return samples to Earth, where they can be studied with powerful instruments. Mars may be dead on the surface, but its past remains alive in its geology. Whether life ever emerged, there remains unanswered. But Mars continues to offer one of the best chances to find evidence of life beyond Earth. Mars and Earth began with many similarities, but their futures diverged dramatically. Understanding why Mars became a dead world while Earth remained alive requires examining the differences that shaped their long-term stability. The answer lies not in a single event, but in a combination of size, internal heat, and planetary protection. Earth is larger than Mars. This difference gave Earth a crucial advantage. Larger planets retain internal heat for much longer periods of time. Earth's molten core continues to generate a strong magnetic field that shields the planet from solar radiation. This magnetic field deflects charged particles from the sun and prevents the atmosphere from being stripped away. Mars, being smaller, cooled faster. As its core solidified, its magnetic field weakened and disappeared. Without this shield, Mars became exposed. The solar wind began eroding the atmosphere relentlessly. Over hundreds of millions of years, Mars lost most of its air. Earth also benefits from active plate tectonics. The movement of tectonic plates recycles carbon dioxide through the crust and mantle. This process stabilizes climate over long timescales. When carbon dioxide increases, it is eventually absorbed by rocks. When it decreases, volcanic activity releases more. This balance keeps Earth within a narrow temperature range suitable for life. Mars does not have active plate tectonics. Its crust became rigid early in its history. Without this recycling system, Mars could not regulate its atmosphere once volcanic activity declined. Gases were lost faster than they were replaced. Water played a critical role as well. Earth's oceans store heat, regulate temperature, and support a complex biosphere that influences atmospheric chemistry. Mars lost most of its water early. Without large oceans, Mars could not buffer climate changes or support long-term biological regulation. The result was a cascade of loss. No magnetic field led to atmospheric erosion. Atmospheric loss led to cooling. Cooling led to water loss. Water loss led to the collapse of habitable environments. Mars crossed a series of thresholds, each one making recovery more difficult than the last. Earth avoided this fate because its size, heat, magnetic field, and geology worked together. Mars did not fail because it lacked potential. It failed because it lacked endurance. Mars teaches that habitability is not only about having the right ingredients. It is about maintaining them over billions of years. Worlds can begin with promise and still lose everything. Even as Mars became cold and lifeless on the surface, it did not lose its importance. In fact, its transformation made it one of the most valuable worlds in the solar system for scientific study. Mars preserves its history in a way Earth does not. On Earth, plate tectonics, erosion, and life constantly reshape the surface, erasing ancient evidence. On Mars, time moves more slowly. Ancient riverbeds, lake sediments, and volcanic plains remain exposed, frozen in place for billions of years. Modern missions to Mars are designed to read this record. Orbiters map the planet in detail, identifying minerals formed by water and regions that once held lakes or groundwater. Rovers travel across ancient terrain, drilling into rocks that formed when Mars was still wet. Each layer tells a story about temperature, chemistry, and habitability. Rovers, such as Curiosity and Perseverance, explore locations chosen specifically because they once held water. Gale Crater contains layered sediments that formed in a long-lived lake. Jezero Crater holds a well-preserved river delta, where sediments accumulated slowly over time. On Earth, such environments are excellent at preserving signs of life. Fine grains can trap organic material and protect it from destruction. These missions search for biosignatures, not living organisms, but chemical and structural clues that life once existed. Scientists analyze organic molecules, mineral patterns, and isotopic ratios that could indicate biological activity. Finding such evidence would not only confirm life on Mars, but demonstrate that life can arise on more than one world. Mars also matters for understanding planetary evolution. It shows how quickly a world can change when protection is lost. It provides a natural laboratory for studying atmospheric loss, climate collapse, and planetary cooling. By studying Mars, scientists learn how atmospheres behave under solar radiation and how long water can survive on a small rocky world. These lessons apply directly to the study of exoplanets orbiting distant stars. Mars also matters because it represents a possible future for many worlds. Not every planet remains active and protected like Earth. Many may follow a path similar to Mars, losing their magnetic fields, atmospheres, and surface water over time. Mars allows scientists to study this outcome in detail, using a real example rather than theory alone. Humanity's interest in Mars is also driven by exploration. Mars is the most accessible planet for future human missions. Understanding its environment, radiation levels, and history helps prepare for long-term exploration. But beyond exploration, Mars holds deeper meaning. It represents a world that nearly succeeded. Mars shows that planets can be habitable without becoming permanently alive. It reminds us that life depends not only on beginnings, but on sustained protection and balance. Each rover mission adds new details to this story, refining our understanding of when Mars changed and how quickly it happened. Mars still matters because it asks a fundamental question. If life arose once, could it arise again? And if it arose on Mars, where did it go? Mars today is quiet, cold, and dry. Dust drifts across empty plains. Ice lies hidden beneath the soil. The sky is thin and pale. From orbit, it looks like a world long abandoned. But Mars remembers. It remembers rivers that carved valleys across its surface. It remembers lakes that filled craters and basins. It remembers a time when water flowed freely and the planet was active and alive with chemical possibility. Mars was not always a dead world, it became one. The story of Mars is not about sudden destruction. It is about slow loss. The loss of a magnetic field, the loss of an atmosphere, the loss of warmth and water. Each step made the next unavoidable. Mars crossed a series of thresholds that led to silence. Mars teaches humanity that planetary survival is fragile. It shows that having the right ingredients is not enough. A world must protect itself over immense spans of time. Without protection, even a planet with rivers and lakes can fade into a frozen desert. As scientists continue to explore Mars, they are not only searching for evidence of past life, they are searching for understanding of how worlds change, understanding of how life survives, and understanding of what makes Earth so rare. Mars is a fossil planet. Its surface preserves a memory of what once was possible. By studying that memory, humanity learns how to recognize habitable worlds and how to protect the one it calls home. If you wish to continue exploring lost worlds, ancient climates, and the hidden history of the universe, remember to subscribe and join us again. The universe leaves clues everywhere. Some are written in rivers. Others are written in dust.